Now, in this presentation, we are going to learn this method of computation of altitudes. Now, we have seen that in celestial observations, we can obtain a position line from a celestial body by taking its site. Taking the site basically means observing the body using a sextant, getting its sextant altitude, then correcting it to find its true altitude. Once we get the true altitude of a body from the sextant, we are able to use it in different formula, in different conditions, and we are able to obtain the position lines. Now, what if I tell you to get the altitude of a body without using the sextant? I tell you we don't have a sextant right now, but you tell me what is the altitude of this particular body which we are able to see. Let us say sun we are seeing. So what is the altitude of the sun without the sextant? Is there any way with which the altitude of the sun can be found or calculated or completed? This is what we call as computation of altitude. That is, obtaining or computing or calculating the altitudes of celestial bodies with calculation, with formula, without actually observing it using a sextant. So this method can be used to obtain the altitude of a body for any future date and time. And with a sextant, with the instrument, you are able to obtain it only in real time. But when you use the computation method, you can calculate the altitude of a body for a future date and time of your requirement, of your choice. So let us now see how do we compute the altitudes of the bodies. If you remember in intercept method, we discussed the intercept method can be used to calculate the zenith distance of a body. You remember we computed the CZD, calculated zenith distance in the intercept method. And from that CZD, calculated zenith distance, we can then obtain the altitude of a body. So intercept method can be used to compute the altitude of the body. So we will see now in detail how in a particular situation we can use that intercept method to compute altitude of a body. Also, we will see that in conditions where intercept method is not used, like say for example in the case of meridian passage, we do not use the intercept method in meridian passage observations, or in case of Polaris or pole star. In Polaris or pole star also, we do not use the intercept method. We use the Polaris correction tables from the almanac. So we will see in those scenarios, how do we compute the altitude of celestial bodies. Now, before I go into the step-by-step procedure of altitude computation, let us first also try to understand that what is the need or requirement of computing the altitudes of celestial bodies. When we can observe them with a sextant, and then we can use that information in our sight to find out the position line, why do we need to compute the altitude of a body? Now, in present times, the computation of altitudes may not be much relevant. It's become little outdated and redundant. But in the olden times, when we were entirely dependent upon celestial navigation as our sole method for position fixing, especially in open sea conditions, that time this computation of altitude was very, very important. Now, why was it important? Now, in those days when there was no GPS, celestial position fixing was an important part of our daily routine. We used to fix up the vessel's position at noontime. We used to take a morning sight, then fix up the vessel's position at noontime. Then we used to take a evening sight during evening twilight, and we used to fix the position of the ship. And basis those fixed position, we used to carry out DR navigation till our next position fixing. And it was important. If we missed a position fixing and there was an error in the DR position, there was a chance that the vessel may run into danger. So taking site was very, very important. Now it may be possible that at the time of site taking, there may be clouds in the sky or fog or rain, because of which the celestial body may not be visible to you. Now, just to give an example, especially in the case of Marpas, now you see Marpas happens in an instant. It happens only once a day. Now, at that time, if there are clouds and the sun is hidden behind those clouds, you will not be able to take the Marpas site. Similar thing happens during the evening twilight also. We have a special period within which the site can be taken. That is, in the evening, it is the end of civil twilight to end of the nautical twilight. If that period is missed, it may be 5 minutes or 10 minutes or 15 minutes. If that period is missed, then site taking will not be possible after that, because the sky or the horizon is going to become dark and we will not be able to obtain the altitude of the body. Now, since we have a limited period to get the site, and if we miss that period, we will miss our position fixing. A usual site, let us say you went out to the bridge wing and you wanted to take a site, will take about at least 4 or 5 minutes, because first you will need to set your sextant depending upon what is the altitude of the body. So you will have to move the swinging arm, set the swinging arm at a certain location at a approximate altitude where the body is. And this setting of the sextant is going to take some time, 2 minutes, 3 minutes, 5 minutes, depending upon your experience and expertise. Now, the advantage of computation of altitude was that if there is cloudy situation and the body appears only for a few moments, let us say you were taking a star sight during evening twilight and the star which you wanted to pick up was behind the clouds, and the clouds opened up and you were able to see the star for some time, let us say for 1 minute, and then later on it again was covered by the clouds. Now, if you were setting your sextant, or if you try to or start setting your sextant at that instant, you may take 2, 3, 4 minutes to set it, and to obtain the site maybe another 1 minute or 2 minutes. So you require to observe the body for this much of time. But if you compute the altitude of the body beforehand, you know your DR position, you know which body you are going to observe. So using these methods, if you compute the altitude of the body beforehand, then you can set your sextant before going out. Before the twilight comes, you can set your sextant to that particular angle. And even if the body is visible to you for half a minute, for 30 seconds, with your sextant, the swinging arm set in the required position, you will only need a few seconds to maybe move the micrometer or the swinging arm to get the sight of the body. So with the sextant already set to the or close to the required altitude, taking the site would require much lesser time. Instead of 5 minutes, you could do it in a matter of 15 seconds. So this was the use and advantage. Before taking every site, we used to compute the altitude of the body. The altitude was computed, we used to calculate it, and we used to set our sextant ready for taking a site. And sometimes we used to have 2 sextants or 3 sextant. Then we will set all 3 of them, and 3 duty officers will be standby holding those 3 sextants. And as soon as the body was visible to us through a break in clouds, the sun or the star, you were able to get the altitude of the body quickly, and that would help you to fix up the position of the ship. This was the aim or the need or the purpose of computing the altitude of the celestial body beforehand and then taking the site quickly to fix up the position of the ship even in cloudy conditions. So this is the theory or the need concept behind this computation of altitude method. Now let us see how do we uh, follow this method step by step, what all information is provided to us, and what is the procedure stepwise which we follow to compute the altitude of the body before taking a site. Now we are going to begin with the computation of altitudes of different celestial bodies at the time of meridian passage. How to compute the altitude of a body at the time of meridian passage? Let us first see what is the information which is provided to us in these questions. We have the date for which the altitude is to be computed. We have the index error. We have the height of I. So these are required for altitude correction. Index error and height of I are provided to us. And we have the dr position. Now, one important thing before we proceed ahead, the computation of altitudes is done basis our dr position. Now, this is the most accurate position which we are aware of, which we know. It is possible that this position may have some error in it because it is a dr dead reckoning position. It may have some error in this. This is not a fix. And because of this error in the dr position, the altitudes which we are computing may also have some error. So they may not exactly match with the actual altitude of the body which we are going to observe, but they will be very, very close to it. So for our purpose of setting the sextant before going ahead with a site, this much accuracy is enough. This is the best what we can calculate in the information provided. Now, if you look at the information provided, which is the date, index error, height of I, and the dr position, you will observe that this is exactly the information which will be available to the duty officer on board a ship when he plans to take a site. This information is available to him, it is known to him, and using this, he can compute the altitude of the body before he goes ahead with the actual site. So let us now see the items which are required. The item which we require here is the meridian altitude of that particular body. This is what is required to be calculated. Now let us see the stepwise procedure. The first thing what we do, as we had done in the meridian passage questions also, we find out the GMT of meridian passage. It is found from the almanac. We have the LMT Marpas mentioned for sun, planets, as well as moon. For stars, it is not required. So from that LMT, we apply the LIT and we get the GMT meridian passage of the body. From this time, we can obtain the declination of the body from the almanac. So declination is obtained. Now let us see what we did in a Marpas question, in a meridian passage question. Now in a meridian passage question, we were given the sextant meridian altitude. This was provided to us in the questions. We applied the index error and the dip correction using the height of I, and we obtained a apparent altitude of the body. Now to this apparent altitude, we applied the total correction picked up from the nautical almanac, and we obtained the true altitude of the body. Now 90 minus true altitude gave us the MZT, which is the meridional zenith distance of the body. This MZT we combined with the declination of the body. So we combined the MZT and declination. In some cases, they were added up. In some cases, one of them was subtracted from the other. And once we combined these two, we got the observed latitude. So this is the procedure which we follow in a meridian passage observation. Now, in this case, we are going to do exactly the reverse of it. We will follow the same procedure exactly in the reverse technique or the reverse way. So instead of starting with sextant altitude, we are going to start with the observed latitude now. Now, from where do we get this observed latitude? It is not possible for us to get the observed lat. So what we do in these questions is we use the dr latitude which is provided. We assume or we calculate basis the dr position. So we start off with the dr latitude at the bottom and we go backwards. You see the direction of the arrow upward means that you start at the bottom with the dr latitude and you proceed upwards. Now let us see how do we proceed ahead. To the dr latitude, we first combine it with the declination of the body. The declination is already obtained from the almanac. So declination and latitude, depending upon their name, are combined. In some cases, they may be added up. In some cases, one may be subtracted from the other. And doing that, we obtain the MZD, meridional zenith distance of the body. Now, once you get the MZD, 90 minus MZD would give us the true altitude of the body. So once the true altitude is obtained, the next thing which we need now to proceed ahead is the total correction. Now there is one problem here which we face. The total correction is obtained from the nautical almanac, from the total correction tables. And this total correction table is entered using the apparent altitude. Now in this case, we do not have the apparent altitude with us. What we have is the true altitude. So how do we obtain the total correction? Now fortunately, in the case of sun and in the case of stars and planets, whether you enter into the table with the true altitude of the body or you enter it with the apparent altitude of the body, this does not make a difference because the total correction is applicable or valid for a range of altitudes, and this range is quite big, whereas the difference between the true altitude and the apparent altitude is not going to be much as compared to the range given in the total correction table. So 99% of the times you will see that the true altitude as well as the apparent altitude, they fall within the same range given in the almanac, giving you the accurate total correction irrespective of whether you enter with apparent altitude or you enter with true altitude of the body. Now, even if we assume that because of this difference in the true altitude and apparent altitude, you entered into the total correction table, you entered in a different range. Even if you enter in a different range, the difference in the total correction is going to be in the range of about 0.1, which is very much acceptable accuracy for the computation of altitude. Whenever we compute our altitudes, we are aware that this computation is done on the basis of the dr position, and there is a possibility of error in these readings. And this is just taken to help us set the sextant so that we can take the site very, very quickly. Even if a small time interval is available to us for site, with the sextant set, we are able to obtain it very, very quickly. That is the whole purpose. We do not use the computed altitude for any calculations. So we are aware that there is a scope of error in this computed altitude. So even if there is a little bit of error by entering the table using the true altitude instead of apparent altitude, that is very much within our acceptable range and accuracy. So you enter the total correction table with true altitude, get the total correction, apply it in the reverse way, and you get the apparent altitude of the body. Now, once the apparent altitude is obtained, we apply the dip correction now. Basis the height of I, which is given to us in the question. We apply the dip correction in the reverse way, and we get the observed altitude. To the observed altitude, we apply the index correction in the reverse way, and once we do that, we get the computed sextant meridian altitude of the body. Now, one important thing to keep in mind, when you are going in the reverse direction, you will be applying the corrections in the opposite order. Let us say the total correction is negative. The total correction is negative. Now, when you are coming down from sextant meridian altitude towards the true altitude, a negative total correction is subtracted. But when you are going in the reverse direction, you are going upwards from true altitude to the sextant altitude. In that case, a negative total correction will be added up. So you will write it as minus here, but you will actually be adding it to the true altitude to get the apparent altitude. Same applies to the dip correction. Dip correction is normally negative, but when you are going upwards in the reverse direction, it will be written as negative here, but going upwards, it will be added up in the calculator to obtain the observed altitude.